Molded pulp and fiber systems face immense pressure to maximize efficiency, especially as sustainable recycled furnish becomes a larger part of the mix. This recycled fiber introduces a persistent operational challenge. Stickies and other contaminants that adhere to equipment surfaces, blind apertures, and disrupt flow. This ultimately reduces drainage efficiency, increases downtime, and drives up maintenance costs. To combat these issues, manufacturers utilize advanced woven wire mesh strategies that go beyond basic filtration. The right mesh design actively resists buildup, maintains open area longer, and handles higher contaminant loads. By fine-tuning aperture size, wire diameter, and weave geometry, operators can improve contaminant release while successfully balancing flow and durability. Stickies are composed of adhesive materials like pressure-sensitive glues, hot melts, latex binders, and waxes recovered from paper streams. They're uniquely deformable and tacky, and unlike typical solids, they physically interact with and adhere to equipment surfaces rather than just passing through. As pulp flows across the screens, these contaminants soften, stick to wire surfaces, and form deposits that quickly bridge across apertures. This restricts flow paths, drops drainage efficiency, and raises pressure differentials. This process directly leads to aperture blinding. Blocked openings prevent water and fiber from moving correctly, resulting in reduced throughput and downstream sheet defects. Recycled furnish amplifies these effects by introducing a higher concentration of stickies that agglomerate under heat, pH shifts, and shear, and because these particles continually evolve and increase in adhesiveness during processing, an optimized contaminant-resistant mesh design is critical. In high sticky systems, mesh selection must focus on maintaining long-term performance by limiting contamination accumulation. Aperture design and wire geometry directly control material flow. While smaller openings improve contaminant capture, they restrict flow and clog easily. Conversely, thicker wires increase structural lifespan but reduce the available open area. High-performance designs find an engineered middle ground that balances openness and contaminant tolerance to sustain consistent throughput. Weave patterns also heavily influence surface interactions. Woven wire mesh naturally creates multiple contact points where deformable adhesives can settle and bridge, whereas alternative geometries, like profile or slotted designs, reduce these contact points and encourage contaminant release. Optimizing the weave style and finish significantly reduces surface energy to prevent stickies from anchoring. To maximize performance, engineered mesh designs focus on several practical principles. They must maximize cleanable open area without sacrificing structural integrity, minimize flat contact surfaces where stickies can adhere, and promote flow paths that discourage particle lodging. Furthermore, these designs should utilize wire geometries that reduce bridging across apertures and maintain consistent shapes under load to avoid deformation-driven clogging. Even well-designed mesh demands a disciplined maintenance approach because contaminants inevitably accumulate. Fouling typically manifests as a gradual increase in pressure drop across the entire mesh surface. As apertures plug, flow resistance increases and capacity drops. If operators try to compensate by increasing pressure or flow rates, they often accelerate wear and force contaminants deeper into the mesh structure. To counteract this, modern maintenance designs combine several strategies, including hydraulic routine flushing and backwashing to remove loose fibers, mechanical dislodging methods utilizing air, vibration, ice blasting, or brushing, and targeted mechanical cleaning to break down adhesive bonds and lower mesh surface energy. Consistency is vital, as delaying intervention until fouling is severe requires aggressive cleaning that shortens mesh life. However, operators must also recognize when cleaning is no longer viable. Frequent blinding, unstable flow, or declining throughput after cleaning cycles usually indicates a design mismatch rather than a maintenance failure. So over time, repeated clogging distorts apertures and weakens wire junctions, yielding diminishing returns on maintenance efforts. In these scenarios, the most effective choice is reevaluating a mesh redesign to adjust aperture size, wire diameter, or weave pattern to perfectly match the furnish's specific contaminant profile. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things Hover and Boker. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.